All right, let's start. Do you have any question? Okay, so last time we were discussing the discrete interest rate model. And we have two models that we were discussing. The Holy model, where we have the R sub k, right, is going to be AK plus BK times UK of omega, so RK of an event. And then we have the Black-Derman toy model, where the interest rate will be AK B sub K, sorry, B sub K raised to UK omega, where UK omega is a number of U's, number of up in the path omega. All right, so the given, right, AK BKs, right, K from 1 up to, let's say, n minus 1, we can populate the interest rate tree and tries, right, interest rate related products.
Professor, we can't see the screen. It just says your screen sharing, but it doesn't show anything.
Oh, apologize.
Yeah.
That's weird. Hold on, give me a moment. Okay, is that better?
Yeah.
Apologies. I didn't realize that the screen wasn't shared. Okay, so okay, maybe walk back, right? So discrete interest rate models, we have the Holy model, okay, like this, or the Black-Derman toy model, where the way that our interest rate is related to a binomial tree is via this UK random variable that counts how many U's in omega, I guess, up to time k. All right, and so the AK, BK are the variable, are the parameters of the model. So up to, what do I want to say here? If we're given, right, these parameters up to time n minus 1, and we can populate the interest rate tree and price interest rate related products up to time n. Okay. So for example, right, the example we considered last time was Holy model. With A0 to be 0.05, A1 to be 0.045, AB1 to be 0.01, A2 to be 0.04, and B2 to be 0.01. So what that means, right, is we have the interest rate tree like this, where R0 is 0.05, R1 up is 0.055, R1 down is 0.045, up is 0.06, up down is 0.05, and down up is 0.04. But right, because the way that it works is interest rate, the rate RK is applied to the period K to K plus 1. So therefore, right, this rate is going to be the available rate for 0 to 1. If you go up here, then it's going to be the rate available from 2 to 3. And if you are here, or here, for example, then it's available from 2 to 3. The point is that, right, this rate, this interest rate tree is good for any investment, okay, in the time period from 0 to 3, not 0 to 2, like the stock tree. If we stop here, then we just can go back to 2. But we stop with interest rate 2, then we can go up to 3, okay? So several things to note that, first of all, okay, there is no risk-neutral calculation, risk-neutral probability calculation for the tree. So in other words, if we work with interest rate model, then it's automatically given in a risk-free model, in a risk-free framework. Oh, sorry, risk-neutral framework. The reason, okay, is that we do not have any tradable product to determine the price independently. So, right, reason is that interest rate is not a tradable product. So we cannot use this tree itself, okay, as a price, as a determination for risk neutral probability. So we must accept that the probabilities are given. So, you know, then we just pick some kind of arbitrary number in terms of the example, right? So we just pick, so for example, probability up is, I think we say 1/3, and probability down to be 2/3. In practice, this can be determined if we have also a stock model next to our interest rate model to help us determine this. But interest rate by itself cannot help us to decide the risk neutral probability. Two, right, in practice, right, of course the AI, AK, BK are not given. Okay, what's given is we instead know the price, okay, of the products, such as the bonds, right? The bonds B0K, B0I, right? I from 1 to N. We know the price of interest rate cap and floors. Okay. And if necessary, we also know the swap rate. But I think the swap rate is already kind of implied by the bond, as you will see. But the point is that, right, these products, the price of these products, theoretically, we establish will be functions of the AKBK. Okay, so these prices theoretically establish to be dependent on AKBK. So what we know, what we can do, right, is knowing these prices, we can decide, or we can estimate, okay, A hat, B hat based on these prices, and this is called model calibration. Okay, so for example, you will see on the homework, right, the last homework of this week, that we have a market with 3 products. You have bond B01, B02, and a cap. Cap with T equals to 2 and strike equals to 0.03. Right? We discussed cap last time. We'll continue to discuss cap. All right. So the prices are given. And then you're asked to decide A0, B0, and A1, B1 in wholly and black dormitory model. So these prices perfectly. Okay. So that's the kind of like the usual kind of a problem that you want a practitioner will face when they have a model and they want to calibrate it with like currently known products. Okay, so like that. So that's where we were at last time. We discussed how to price bond, right? We can rewrite the equation, and then we'll move on to the cap and floor, and then talk about swap rate. Do you have any questions? All right, so let's see. So pricing bonds, right? So basically, pricing bonds is pretty simple. A bond B0T, right? Let's say B0N, right? Pays $1 at time N. So this bond price at time 0 will be the risk neutral expectation of just discount all the way back, right? 1 over 1 plus Ri delta T, or I from 0 to N minus 1. That's all, right? You just discount all the way back, right? And each of this is a discount factor over each period. Of course, you saw like with what we did last time, right? That the way you actually carry it out is through a table, right? A table of events. Okay, so you would write omega, right? 1 plus. So 1 plus R1. So omega, I guess you do R1, right? R0, R1 up to Rn minus 1. and then you would do the discount factor, right? And then the probability. So for example, you would do UU, UD, DU, DD, right? You would fill this out. So, and then you would calculate all these, and you would add them up at the end, right? So that's the bond. What about interest rate caps and floor? So interest rate caps, right, is like a call option. On the rate, right? So we want to remember, right? So interest rate cap also has two components, right? It has an expiration. Oh, it has, yeah, it has an expiration, right? And then a strike K. But I prefer to think of it as the expiration here, right? We should think of it as more like a investment period. Let's say from 0 to n, right? Because what that means is unlike a call option where you get one payment at time n, when people say cap, it really is about a series of payment, right? Interest rate works like that. The reason is, I guess, throughout, right? When you look at from 0 to n, there are many sub-time periods as dictated by the model or dictated by the way we the way we want to structure our investment. So from time 0 to time 1, you should receive some payment. From time 1 to time 2, you should receive some payment, so on and so forth, right? And so what are these payments? Well, these payments, right, will be decided by the fluctuation between the interest rate, the actual interest rate, and the cap, right? Cap level, okay. So from time 0 to time 1, you will receive this amount, meaning you will receive the compensation, right, if the rate is above K for this investment period. And so maybe let me do this, right? So this is the payment at time 1. And the payment at time 2 is very similar. It will be R1 minus K plus delta T, so on and so forth, right? All the way up to you receive your last payment here, which is Rn minus 1, right? Sorry, minus K plus times delta T. So what do you do? What do you do? How do you find the price, right? So the price. Oh, and also, right. So there's also a corresponding idea of a caplet, right? A caplet, let's say with expiry n and strike K, has only one single investment period. Okay, so actually a caplet is the closest we can think of as in terms of the call option. And what it does, right, is it just pays you exactly, right? So here n minus 1 to n, it pays you this single amount at time n. So a cap, right? So what we think of, so this product right here on top, we will denote it as cap 0 n. Okay, and this we will denote as caplet 0 n, right? So then when we write like this, it's compact, but pay attention, right? The name says about the product. So a cap, right? Same notation. It really means a series of payment all the way from time 1 to time n for the cap. The caplet, right? Even though it says 0 to n, 0 only refers to now as the time that we are looking at the price of this guy. But the n, right, or the caplet itself says that you only have one single payment at time n. Anyway, but if we understand the meaning of this notation or these names, then it's very simple to write something like this. A cap can be broken down as a bunch of caplet. Like that, right? And so basically this simplifies the task. So to price, right, to price the price of a cap, we just have to price the price of the caplets and add them up. So let's look at one example, right? And the example is easy. Let's say we have the Holy model that we looked at before. And let's look at the price of a caplet, right? Let's look at a caplet. 0.03 with strike k equal to 0.05. So again, right? So here's the tree model. The tree model is 0.05, 0.06, 0.0. Oh, sorry. This is the black movement toy. Give me one moment. 0.055, 0.045, 0.06, 0.05, 0.04. Okay, so this is R. Okay. All right, so caplet 03 will make a payment here, right? And the payment is the difference between this guy and 0.05. So let's take a look first, right? So payment, if you want, and then maybe let's do event first, right? So table, actually table is very easy. Event, payment, and prop. So the event, right, is UU, UD, and DU. UD and DU are the same, right? So let's say UD and DU and DD. So what's the payment here, right? The payment is 0.01, 0, and 0 because it's a cap, right? The cap will strike 0.05. And so the probability, right, is only the PU up, which is, I think, 1/3 square. Because we say that the probability of going up, the risk neutral probability of going up is 1/3, right? So like that, right? So, okay, so we have one single payment with this probability. But of course, right, this payment is the payment made at time 0.01. Oh, sorry, what am I saying? Payment at time 3. So we need a discount factor, right? You need a discount factor. So the discount factor is exactly the discount factor corresponding to the up event. So we need exactly, 1 over, right? 1 plus R0, 1 plus R1 delta T, etc. Right? So I'll just write down the actual number, but the discount here will be, let's suppose delta T equals to 1 here, right? To make things easy. So it's going to be 1.05 times 1.055 times 1.06, right? That's the discount factor. And so all in all, right? So the price of a caplet in this exact event will be, right, 0.01 times 1/3 square, and then divided by all this discount. That's a caplet for this strike. Any question on this? Okay, so now suppose that you repeat the question, right, but with the cap. Like that. So what are we asking? So what we're asking, right, is, I think you can just go with the definition, but I think it's kind of complicated. So basically, it's best to separate this cap into caplet, right, 0.1 plus caplet 0.2 plus caplet 0.3, right? So we have, basically this question asks us to price 3 caplets, right? Now, what's the caplet 0.1? Caplet 0.1 exactly is the payment at time 1, right? Where how much? What's our tree? Our tree at time 1 is 0.055. Oh, sorry. The caplet at time 1 pays us, right? Remember, so it's 0.05 and it pays us R0 minus K plus. But because R0 is 0.05 and the strike is 0.05, right? Caplet 0.1, the price is 0. There's no payment there, right? There's no payment on either event. Then caplet 0.2 will pay you, right, the 3, so from these 2 branches, right, it'll pay you so if this is here, right, then it'll pay you 0.05, 0.015, right? Here it also pays you 0.015. But so I think here, right, there is a, give me a moment. So if you end up here, right, then you get paid this much at time 3, but oh, I think there's only 2 events, sorry, apologize. So maybe let me just do the event, it's easier that way. So for caplet 0.2, right, you also do an event. So omega, right, payment and prop and discount. And so omega has only 2 types, 0D or U or D. If it goes up, then you got a payment of 0.005, right? And the probability is 1/3. And the discount is the 1 over, right, this and this. So there's going to be 1 over 1.05, 1 over 1.055. D, there's no payment, so we don't have to care about that. And then so the caplet 0.2 will be, right, 1/3 times 0.005, and then like that. Okay. So that's going to be the way that you would price caplet. And then you would add all these answers together with the caplet you found before, and you'll get the cap price in total. Any question here? Okay, so pretty straightforward, right? The only thing to remember is the caplet and the cap, right? With the series of payment. So pricing of floorlet, floor, right, and floorlet are the same. Except you want to remember, right? So this is the cap is the call option. This is the put option, right? So I'll skip the example unless you want me to do some here. Okay, so let's look at the next one, which is like the forward contract, right? So we kind of cover exactly the same analog in the option. There's the bond is, I'm not sure what bond is, right? Bond is just bond. But the other ones, like the cap and the floor, are like call put option. And the forward is like a forward option. So for a contract, except that, right? Forward here always is understood as the one that makes the price to enter zero. So in other words, this should be called a forward rate agreement. Or FAR. And together with this, there's something called a swap. And together with this, there's a swap rate. Okay. And so actually the relation between these two are similar to the the floorlet. So this is the cap and caplet. So this is like cap, and this is like caplet. So in other words, the swap rates are like for investment over multiple periods. The forward or forward rate agreement is for investment over one single period. So maybe let me put it that way. One period. One single period. Is the sort of notation, the name is called a forward rate agreement, and the swap rate is for multiple period. Okay. So what's the story there? The story is actually the same thing, but here, right, you just swap the rates, right? So it's typical in this situation to refer to one of the, so let's look at the investment period, right? 0, 1, 2, let's say, and then up to n. Okay. So let's look at if you have the forward rate agreement, okay, let's say over the period n minus 1 to n. All right, so that's like a caplet. What happens is is either way, right? You can pay the variable rate, which is, right, obviously Rn minus 1. And then you will receive the fixed rate, which is, whatever the rate that's determined upon. So let's call it F, okay? F for forward rate. So the point though is that whatever this structure is, right, F should be decided so that, right, this is free to enter. At time 0. It's free to enter as time 0. So the point is F is structured, right? so that it's free to enter. Okay, so this is like the forward price, right? But in this context, because it's the price on the rate, so we call it the forward rate agreement. Okay, forward rate. And so what is this forward rate, right? What is this forward rate? So to decide, right, how to decide F? How to decide F? Well, we just need to look at right, so it's typical to refer to one of them as a fixed leg payment, and a variable leg. And make sure they're equal. In value at time 0. Okay, because basically, right, what happens is, because it's free to enter, that means that if with the F rate like this, a investor doesn't care if they have to pay the fixed rate or they have to pay the variable rate, okay, at time 0. And by the way, right, so you understand the idea here. If you agree to get a fixed rate, what that means is that you will know the rate that you will pay in advance in this time period by time 0. So you will know this rate at time 0. Let's say you pay 3%. On the other hand, right, if you agree to the variable rate, what that means is you do not know this rate until the time of the investment, right? Then that rate will be announced to you. Okay, that's the difference, right? So the fixed rate, you know, at time 0, but of course you only start paying it at time n, right? Investing in time n minus 1 to n. The variable rate you do not know until time n minus 1, until you start the investment, then you know the rate. Anyway, right? These two should be structured so that either way you don't care. So how does that work? Well, it works through the bond, right? So like this. So what is the fixed rate payment? The fixed leg, right? The fixed leg, what makes one single payment, right? Or receive one single value at this time, at time n. And the value is this F, right? So the fixed leg receives F times delta t at time n, right? So the value of this fixed leg at time 0 would be F delta t times B0n. Do you agree? So that's the value of this fixed leg at time 0. On the other hand, right, what about the variable leg? The variable leg is kind of interesting, right? It starts, so it receives Rn minus 1 times delta t, right, at time n, right? It receives this much. How do we price this, right? How do we price this? So the value at time 0 seems like, something like this, which is the risk neutral expectation of, right, discounting product, right? 1 plus R I delta t, I from 0 to n minus 1, and Rn minus 1 delta t, like that. Okay. So that looks like a scary expression, no? That looks like a scary expression, except that that's not really true. The reason is, right, one of these terms right here is Rn minus 1, okay? So let me demonstrate to you, right, make it easy. So suppose n equal to 3, okay, to make it easy. What is this calculation? This calculation says you want to take the risk neutral expectation of, right, R2, right, delta t, and the discount factor is 1 plus R0 delta t, 1 plus R1 delta t, 1 plus R2 delta t, like that, okay? And this right here just makes you want to do what? 1 plus and minus. Yes, you just do 1 plus and minus. And so if you do that, what do you get? If you do 1 plus and minus, right, so let me do this. 1 plus R2 delta t minus 1. And then, right, let me just write same. It's too many to write. Well, if you just look at the 1 plus term, then it cancels exactly with this, right? And you only have these two factors left. So basically you got E tilde of 1 over 1 plus R0 delta t, 1 plus R1 delta t, and the other one will be 1 over, right, over 3 periods. Is that okay? But this actually becomes a very beautiful thing, because what is this? This is just what we call the bond price to be paid time 2. And this is the bond price to be paid at time 3. Is that okay? And so what we're saying, right, is the variable leg, the value at time 0, the variable leg is just this difference. Notice, right, that this difference is positive. Why? Because the bond price at 0.2 is always bigger than the bond price 0.3, right? It's a shorter maturity. So, or sorry, right here, actually, I have the abstract setup. So it should be bond price at 0 n minus 1 minus the bond price at 0 n. Okay. So actually, right, this whole argument tells us that there's maybe a simpler way to explain this thing. So simpler explanation. For the variable leg. Right. So suppose that you know that you have to make a interest rate payment at this time, right? For well, with this rate for someone, what would you do, right? Suppose that an investor, right, knows that, suppose they are on the variable leg, so they have to make this payment to someone. What would they do? What they would do, right, is they have $1. They will deposit $1 here, right, at that time n minus 1. By time n, what they get, right, they get $1 back, plus, right, plus the interest payment, which is Rn minus 1 delta t. Of course, right, this will go to the investor. This will go to the payment, right? This will go to pay their obligation, right? Pay the obligation for the variable rate. So the cost, right, the value of this whole thing to the investor is what? They put $1 in at this time, they get $1 out at this time. So from the point of view at time zero, what would the investor see as the cost for this whole operation? The cost for this whole operation for him is exactly this value minus this value. That's it, right? That's this whole complicated calculation. It's just expressing this simple idea of, right, to get the variable rate, you deposit at time n minus 1, and you just take out the money at time n and forget the variable rate, right? Forget the interest rate payment. What's that cost to you? This is this cost, which means exactly that must be the one that you forego. Is that okay? And so, long story short, right, the forward rate, right, the fixed leg will tell you, right, sorry, my iPad's frozen. Okay, you can still see the screen, right? So this is a variable rate payment. Okay, so the fixed rate payment, the value is this much. So the forward rate, right, must satisfy the fixed rate payment equals to the variable rate payment. Okay, and so this, right, again, just keep in mind, this is an equation at time zero, right? This is the equation for their value at time zero. Okay, this is an equation for their value at time zero. But that's easy to solve for the F then. So the variable rate is, oh, sorry, the forward rate, right, will be this. So that's a forward rate. Any question? All right. So I want to say one thing, right? So technically speaking, because you could, right, put in any period of investment, to clarify this notation, maybe we should put it as F0 n minus 1. It's a little bit cumbersome, right? But this clarifies all the information that we want. For example, this says that we start the investment at time n. What am I saying? N minus 1n, right? We start the investment at time n minus 1, end the investment at time n, and the value, right, that we want to look at is time 0, okay? So the second thing I want to say is this, that the forward rate is completely determined by the bond price. Okay? So in other words, if you know the bond prices of all maturities, then you would know the forward rate of all maturities, and also for that matter, the swap rate. Okay? So remember, right, two things when I said before, in terms of calibration, right, in terms of calibration, right, in terms of calibration, the model parameters are not given. You're given the price of the products. And then you use this price, right, to decide the parameters. But what products are you looking at? The bonds for sure, caps and floor for sure. And you may think of throwing in the swap rates or the forward rate. But you see, these are redundant because bonds and swap rates are kind of one and the same thing, in the sense that if you know one, you know the other, right? So that's one thing. The second thing I was saying, right, is in terms of the analog, right, for what we do for pricing, right, interest rate derivatives, we have cap, which is like call option. We have floor, which is like put option, and then we have forward rate agreement, which is like right forward contract, but and swap, right, which is like forward contract. But we also have this little product called a bond, right, which is kind of something seems to be special on its own. But this little calculation shows that bond is in effect, right, a bond is in effect a something related to forward rate agreement or swap rate. So bond and forward contract are one and the same thing in some way, right? So in fact, like there are three fundamental products again: call, put, and forward contract, right? Forward contract and the bond in the context of interest rate is like a forward contract in some way via right this relationship. Okay. So even though it seems like the four products, they're just like three essential products in a way. Any question? All right. So let's finish right the story with the swap rate. So the swap rate, right, and let's maybe call it S for swap. What is it? So the swap rate is like the cap and or the floor. So you need to specify the entire period of investment. Let's say 0 to n. Okay. And so a swap is like a series of forward rate agreement. So a swap or interest rate swap, okay? The product is called interest rate swap. Is a series of forward rate agreement. Okay, so it's just like a cap is a series of caplet, right? A floor is a series of forward. Interest rate swap is a series of forward rate agreement. Okay, so obviously saying that doesn't mean that the swap rate is equal to forward rate, right? Because they're different things. So maybe I should say that, right? Doesn't mean, right? Is the same as the forward rate. I guess unless, right, unless the investment period, right, unless the swap itself is the forward rate agreement. Meaning if you have a swap that has only one period, then of course, by definition, it's a forward rate agreement. And so by definition, right, they're the same two rates that are same. But in general, right, when you look at the forward rate agreement on each period, right, they should have different rates, right? While the swap rate is a grand rate for the whole entire period. So basically, again, right, what's the story? The story is one party pays this fixed leg, right? And one party, so fixed leg with rate S, and one party pays a variable rate, right? It's just RK throughout, right? So basically at time one, depends on which direction you go, you would have something like S minus R0 times delta T, right? So here, I guess you pay the variable rate and you receive the fixed rate, right? And then so on and so forth. At time n minus 2, you got S minus, right, Rn minus 3 times delta T. And finally, at time n, you got S minus Rn minus 1 times delta T, right? Like that. And of course, right, your counterparty will receive exactly the negative of this amount because, you swap between you two. Okay, and then again, right, this contract should be structured so that the value at time 0 for each of the party is 0. In other words, right, you don't care if you are on the variable leg or the receiving leg, or the fixed leg. I want to say this, right? When I say you don't care, that means that the investor does not care in terms of the payment stream itself. In practice, there are some incentives that one party would want to choose a fixed leg and one party would want to choose a variable leg, due to their credit worthiness account stuff. Those considerations, you can look into that in a business class, right? We won't go into that, but right, if they're indifferent, then who would even do this to begin with? So when we say you don't care, that means in terms of value, right? In terms of the income stream. In practice, there's some other incentives, right, that push one to the fixed leg and push the other one to the variable legs. Maybe they have some better, again, like a way to obtain this rate. So they would want to enter like different swaps at different times with different parties. Anyway, right? Our job here is just to pure and simple, right? Decide the S. So we want to decide, right, S for the time investment period. Zero N. Okay. So what do we do? Well, again, right, the idea is to find the fixed leg payment value at time 0, and you make it equal to the variable leg payment value at time 0. Okay, and you set them equal, you get it. So what is the fixed leg payment value at time 0? Well, so at each step, right, you pay S delta T, right? At each step, you pay S delta T. So in general, you see it should be S delta T times this, B0I, I from 1 to N. So that's fixed leg value. Is that okay? I hope you see where this comes from. So basically, right, oops. So from 0 to T, right, you have, so S delta T starting at time 1. And if you discount it back, you multiply B01, right? And S delta T at time 2, if you discount it back, you got B02, right? And finally, you got S delta T here. Sorry, right, that's time N. And if you discount it back, you got B0N. So that's a fixed leg. What about the variable leg? Surprisingly, if you follow what's going on so far, the variable leg payment will be 1 minus B0N. Okay. Now it sounds complicated, right? I mean, how could you just have some simple thing like that for the variable leg payment, right? Because remember, right, at time 0 to time 1, that person must pay R0 delta T. At time 1 to time 2, that person must pay R1 delta T, R2 delta T, Rn minus 1 delta T, etc., right? And all these are random, right? Random. You don't know them until you enter this time investment period. Well, the point is this though, right? Exactly because they are the rate available at that time, the investor can just do this, right? At time 0, he just put in $1, right? He would invest $1. At time 1, right, it used interest. He used this to pay the counterparty. Then he has $1 left. He exactly deposit $1. At time 2, he has this. He used this to pay the counterparty, and he has $1 left. So on and so forth, right? All the way to in the end, if you follow this investment stream, at the end, right, he would completely, right, fulfill his duty, his obligation of paying, right, the variable rate, and he will receive $1 back. But right, so from his point of view, to pay the variable rate, all he has to do is just invest $1 and just take it out and put it and redeposit it, reinvest it at every time period. And so the cost of that to him, right, is that his dollar, right, has been traveling all the way through time and lose value. So right, exactly, to see the value he lost is $1, which is this $1, subtract the future value, right, or the current value of this one, and that's it. So that's the variable leg payment. And so all in all, right, these two should be equal in the sense that S delta T sum B0I I from 1 to n must be 1 minus B0n, or S will be 1 minus B0n divided by sum of B0I I from 1 to n, like that. Oh, sorry, I missed delta T, right? They put the delta T inside, doesn't matter. Is that okay? Any question? So just one small remark. Putting delta T inside like this is actually more useful. The reason is, right, in our model, we consider a very special case where the investment periods have all equal length, right? And in practice, you see it doesn't have to. You could structure an investment where, let's say the first investment period is 3 months, the second one is 6 months, the last one is 1 month, right? Whatever. So in that sense, right, each of these delta T will be different. But if you follow our argument, there's nothing that would change that. It doesn't change anything so much, except that you must keep the length of the investment inside the sum rather than outside. Everything else will be the same. This will still be the same, surprisingly. So the variable leg payment is still the same. The fixed leg payment will change in terms of the delta T being inside. So the best thing to do is just keep it inside like this, right? But most of the time, this interest rate swap is structured on equal investment periods anyway. So, okay. Question. All right. So that's really it, right, for the discrete rate model. Discrete interest rate model. So normally I might have time, right, to do the continuous time interest rate model, but I guess obviously we don't have time to kind of do anything seriously there. So we skip that, all right. And so this is the last material for the final exam. I'll talk about the final exam real quick, but let me just tell you, if we have time, what we would cover in this class, right, for the continuous interest rate model. So for the continuous interest rate model, we don't really do much anyway, because the math there is quite involved. But at least we'll do two things. That we talk about, Vasicek and CIR, right? Which we discussed briefly before, and they're quite really important models. All right, they are, as far as I'm aware, they are even more popular, right, than the Black-Dermond-Toy and the Holy model in the discrete time. People like to use these continuous time rate models. And then what we'll do mathematically is we will try to solve for the Vasicek model explicitly. And believe it or not, you have the tools to do it already with all the Ito calculus formula I show you, right? You already can do this. You can solve for this explicitly by yourself. CIR model, as far as I can tell, does not have a explicit solution. what we can do next is we can solve for the expectation, okay? Meaning the average rate of both of these guys. And you'll see a surprising conclusion that both CIR and FIC check have the same expectation. But on the other hand, we can also do something cool. We solve for the variance. Okay. And you see that the variance of these two are not the same. So if you have seen something in along the line of like time series, basically the first moment, right, of these two time series are the same, but the second moment, right, are different. And of course the correlation will be different. So, but we don't look into that, right? And of course, this is scratching the surface, and usually this is where we stop for this class. But then you go on and use these models for pricing, for pricing the bond, pricing the cap and caplet, the forward rate agreement, that kind of stuff. And there are tons of complicated discussion, right, along the line of what happens when we use these continuous rate models. But again, right, that's for the master level class. Okay, so again, we will stop at discrete interest rate model. Hopefully, give you some taste on what kind of things can be done, not just on the stock world, but also on the interest rate world, and that's a very rich thing to be investigated there. Okay, so for the final exam, right? I forgot the date. Does anyone know? It's on the syllabus. Let me just maybe let me just say syllabus for time. Okay. So same format as before. Responders will be required, and then you do submission on a different version. Instance. You can have 2 pages of notes. The format is the same, so constraint is the same restriction. The exam will be cumulative. All right, so I think the new components, right, are the Greeks, right, the Black-Scholes PDE, and the discrete interest rate models that we cover after midterm 2. But you may see also, right, everything that we discover. So we discussed so far, like Ito calculus, discrete model for option pricing, that kind of thing. So I would say it's kind of equally spread. All right, like I don't think I'll put emphasis on any of the material in particular. The exam should be 3 hours, right? I mean, the exam is for 3 hours. I don't plan to put as many questions. Should be like, half of the time more than the midterm. So you should be able to finish in 2 hours. Okay. So the number of questions is like going to be 1/2 more or 1/3 more than the usual midterm. Okay. And that's really it for the final exam. If you have, I will still hold office hours. So Thursday, this Thursday, and next Tuesday. In other time, if you want to send me questions via email, whatever, feel free, and I'll answer your questions by email as well. All right. Any last minute question for me? All right. So thanks for attending the course, and have a good winter break. Yeah, thank you. Is that's not true? We have Friday class. I thought Friday is already a reading day, right? If I'm wrong, if I'm cheating you out of one class, let me know. I think Friday is already reading day, right? Can anyone confirm that? Or they already left? Let me see, right? You can go on to look for the Rutgers schedule, right? Let's see. Rutgers academic schedule. So, oh, this is Camden. Rutgers, New Brunswick. So for exam week, so reading days is Friday, December 11th. Yep. Regular class ends December 10th. Regular class ends December 10th, Dylan. So yes, right. I mean, our Friday class will be December 11th, and that's already reading days. So reading days are December 11th and December 14th. All right. So yeah, this is our last class. Oh, thank you. Appreciate it. Thank you for attending throughout. You know, you're one of the few that are dedicated to go to class. Without you, I cannot lecture. All right. Yeah, thank you, Dylan. Appreciate it. Yeah, see you.